At 3:45 in the afternoon on August 12, 2026, a column of molten rock shot 500 feet into the air above Hawaii. The plume above it climbed to 18,000 feet, higher than most commercial flights cruise over mountain ranges, and began drifting southwest, carrying volcanic glass fibers thin enough to float on the wind for miles, along with sulfur dioxide gas that turns to acid when it mixes with moisture in your lungs. This is episode 53, and what makes that number remarkable isn't the eruption itself. Kilauea erupts constantly. It has, in one form or another, since 1983. What makes episode 53 extraordinary is what it represents inside the longest, most intense, most scientifically documented episodic fountaining eruption in the written history of this volcano. In December 2024, Kilauea started so methane that has now produced more individual eruption episodes than any single eruption in this volcano's recorded history, and it just broke a record that stood for 40 years. Here's what's actually happening inside that crater, why it keeps going, and what comes next. Start with what happened on August 12th, because the sequence that led to episode 53 is exactly the sequence that led to the previous 52, and understanding that pattern is the key to understanding the entire eruption. Around 11:20 a.m. Hawaii time, something started moving inside Halemaʻumaʻu crater at the summit of Kilauea. Lava began intermittently overflowing from the North H vent, the primary source of activity since December 2024. A second overflow started at 11:35 a.m. and lasted about 4 minutes. The Hawaiian Volcano Observatory, which monitors this mountain around the clock with an array of tilt meters, seismometers, gas sensors, GPS receiver, and live webcams, saw exactly what it was looking at. Summit inflation was still continuing. The volcano was pressurizing. HVO raised the alert level for Kilauea from advisory to watch and elevated the aviation color code from yellow to orange, forecasting that full fountaining would begin sometime between August 12th and 13th. At 3:45 p.m., the north vent transitioned from low-level overflow to full eruption. Within 30 minutes, fountains were reaching 250 feet above the crater floor. By 4:38 p.m., the north vent was pushing lava 400 feet into the air, and the plume above it had climbed to 16,000 feet above sea level. Then it kept growing. By the time HVO issued its notice at 5:45 p.m., peak fountain heights had reached 500 feet above ground level, roughly the height of a 40-story building, erupting straight up out of a vent in an active volcanics. Med, after the Hawaiian volcano goddess, formed when lava is stretched by the force of the eruption, southwest across the landscape of Hawaii Volcanoes National Park and beyond. HVO confirmed all eruptive activity was confined to Halemaʻumaʻu crater within the park. No threat to surrounding communities. Alert level watch, aviation code orange. Episode 53 was running. Tying back to inflation as the shallow magma reservoir beneath the summit begins refilling from the mantle below. That refilling takes anywhere from a few days to a few weeks. When enough pressure has reaccumulated, the pattern repeats. Precursory overflow, then full fountaining, then abrupt cessation, then inflation begins again. This cycle has now completed 53 times. The significance becomes clear against the only real historical comparison point for this kind of eruption at Kilauea. From January 1983 to July 1986, the Puʻuʻōʻō eruption on Kilauea's East Rift zone produced 47 high fountaining episodes over 3.5 years. Those eruptions were spectacular, fountains reaching 510 meters, lava flows eventually covering 40 square kilometers of terrain, a cone built at 255 meters above the pre-eruption surface. The 1983 to 1986 Puʻuʻōʻō phase stood as the record holder for the most episodic fountaining events in a single Kilauea eruption in the entire written historical record for over 40 years. The current Halemaʻumaʻu eruption tied that record at 47 episodes. In May 2026, after only a year and a half, less than half the time it took Puʻuʻōʻō to reach the same number. Episode 48, which began on June 1st, 2026, broke the record outright. And now episode 53 is running, 6 episodes past the old record and still going. There's a second record embedded inside this one. The current eruption has produced lava fountains reaching 1,670 feet in its tallest episode. The Puʻuʻōʻō eruptions, for all their spectacle, peaked RO on 1,670 feet during their most intense episodes. Halemaʻumaʻu has surpassed that height too. For context, 770 feet of lava fountain means molten rock is being launched higher than the Empire State Building, plus roughly 400 adedas, honal feet of building stacked on top of it. Not spattered, not slowly rising, launched by gas pressure building inside a magma column, pressurized by the continuous delivery of fresh melt from a hot spot that has been feeding this volcano for hundreds of thousands of years. Now go deeper into what's actually driving this, because the science behind why Kilauea erupts the way it does isn't well understood outside volcanology. And this eruption has added genuinely new data to that understanding. Kilauea sits above a mantle hotspot, a plume of anomalously hot rock rising from deep within the Earth's mantle, independent of any plate boundary. That hotspot has a LD roughly the same position for tens of millions of years, while the Pacific plate has slowly moved over it, producing the chain of islands and seamounts stretching across the Pacific. Hawaii is the youngest, largest, and most volcanically active land on that chain because it currently sits directly above the hotspot. Magma rises through the mantle into a network of storage reservoirs and conduits beneath Kilauea's summit, then flows into the rift zones or erupts at the summit itself. What HVO has been measuring throughout this eruption is a magma supply rate running approximately 25% above the long-term average for this volcano. The preliminary supply rate for the current Halemaʻumaʻu eruption is about 4.4 cubic meters per second. In physical terms, that's a cube of molten rock roughly 1.6 meters on each side, slightly taller than a person, being delivered from the man. That elevated supply rate explains the remarkable tempo of this eruption. The average pause between episodes has been about 10 days. Compare that to Puʻuʻōʻō, where the average pause was 24 days. The current system is filling and refilling roughly 2.5 times faster than Puʻuʻōʻō did, directly consistent with a magma supply running above baseline. Each time the reservoir reaches critical pressure, fountaining begins. Each time the reservoir drains during a fountaining episode, activity stops abruptly. HVO describes these endings as sudden, almost switch-like, activity going from full fountaining to essentially nothing within minutes before refilling begins again. This is also why HVO can forecast episodes days in advance. The tiltmeter network around the summit provides continuous, high-resolution measurements of ground deformation. As the shallow magma reservoir inflates, the ground above it rises in measurable increments, tracked in microradians, tiny angular measurements of the ground surface. Before episode 53, the summit had recovered approximately 10 microradians of inflation since episode 52 ended on July the 29th. That recovery, combined with the rate of ongoing inflation, allowed the observatory to issue its forecast window several days ahead of time. That predictive capability is one of the genuine scientific achievements of the modern monitoring network at Kilauea, and IT has practical consequences. National Park staff and emergency managers can prepare accordingly, and visitors hoping to see active fountaining can time their trips with real reliability. Episode 52, immediately before this latest eruption, ran from July 28th at 7:10 p.m. to July 29th at 2:36 a.m., about 7.5 hours. The north vent reached a maximum fountain height of roughly 500 feet. The south vent didn't fountain in during that episode, but did emit flames near the end of activity. The plume reached about 19,000 feet above sea level. That episode was notably shorter and lower than some of the more dramatic recent episodes. Episode 51 had reached 50 feet, nearly twice episode 52's peak. That variability from episode to episode is itself scientifically significant, because it tells researchers how the geometry of the plumbing system changes with each discharge cycle. Some episodes drain more of the available reservoir than others. Some tap into pockets of more gas-rich magma that produce taller, more forceful fountains. The south vent's inconsistent behavior, sometimes fountain alongside the north vent, sometimes emitting only flames, sometimes doing almost nothing, reflects the branching complexity of the conduit system beneath the crater floor. The hazards tied to episode 53 are real and specific, and they matter for anyone living on or visiting the Big Island. The most immediate hazard during any fountaining episode is tephra fall, the rain of volcanic material ejected from the vents and carried downwind. Tephra ranges from volcanic ash, fine glass and mineral particles less than 2 millimeters across, to Pele's hair, thin glassy fibers, sometimes several centimeters long, that can become airborne and travel significant distances. During episode 44 in April 2026, which produced fountains reaching about 800 feet, reticulite, a lightweight volcanic GL. Ass, similar to pumice, fell in chunks up to 12 inches across near Kilauea military camp, several kilometers from the vents. Highway 11, a main road near the volcano, was temporarily closed due to tephra accumulation on the road's surface, and the National Park's visitor overlooks closest to the active vents were also closed during that episode. For episode 53, Wit, H winds out of the northeast. Tephra and volcanic gas are being carried southwest toward the southwest rift zone and downslope toward coastal communities in that direction. HVO and the National Weather Service track this in real time using wind models, satellite imagery, and ground sensor data to monitor where the plume is moving and at what concentration. Sulfur dioxide from the eruption reacts with atmospheric moisture and sunlight to form sulfuric acid aerosol, which creates the VOG, volcanic air pollution, that affects air quality across much of the Big Island whenever Kilauea is actively erupting. During active episodes, SO2 concentrations near the vents can reach levels immediately dangerous to human health. Even 9 kilometers downwind VOG can cause respiratory problems, headaches, and eye irritation, particularly for people with asthma, heart conditions, or other respiratory vulnerabilities. HVO advises residents and visitors in downwind areas to minimize outdoor exposure and, if they rely on rooftop water catchment systems, to disconnect them during and immediately after active episodes to prevent collecting volcanic contaminants. There's also a slower, longer-running hazard tied to the cumulative lava production of this eruption. Since December 23, 2024, 53 episodes of fountaining have progressively built up the floor of Halemaʻumaʻu crater. Before and after Sate, light imagery shows the crater filling with each episode. The cone forming at the north vent has added roughly 150 feet to the elevation of that part of the crater rim. The total volume of lava produced across all 53 episodes represents a substantial amount of new rock added to the surface of the volcano. All of it has remained confined within Halemaʻumaʻu and the southwest side of Kilauea's summit caldera, which is why there's been no direct threat to surrounding communities, but the ongoing accumulation changes the geometry of the system, which is exactly why HVO monitors it so closely. If lava were ever to fill the sea raider to the point of overflowing the rim and flowing down the flanks of the summit toward inhabited areas, the hazard profile would change significantly. That scenario isn't currently anticipated, but the progressive filling is a real, ongoing process scientists are actively tracking. The question everyone asks, and the one USGS answers carefully and precisely, is how long this will continue. The honest answer is nobody knows. What scientists can say is that as long as the summit keeps reinflating between episodes, and the magma supply from the hotspot stays elevated above baseline, the episodic pattern is likely to continue. The Puʻuʻōʻō eruption that ran from 1983 to 1986 eventually transitioned from episodic high fountaining to continuous low-level effusion when the conduit beneath the vent reorganized. That transition happened relatively quickly and without much warning. Episode 47 ended, and episode 48 began as a completely different style of activity entirely, with lava pouring from a new nearby vent and flowing continuously rather than fountaining episodically. Something analogous could happen at Halemaʻumaʻu, or the eruption could stop entirely, or it could continue in the same episodic pattern for months or years more. The monitoring data will show the transition when it begins, but the current network can't predict in advance which of those paths this eruption will ultimately take. Here's what's certain right now. Episode 53 is the latest chapter in the most prolific episodic eruption in Kilauea's documented history. A volcano that's been erupting in some form for essentially the entire span of recorded human habitation of Hawaii has, in under 2 years, produced more discrete fountaining episodes from a single eruption than any previous eruption in the written record. Each episode has been preceded by measurable inflation, forecast by instruments sensitive enough to detect millimeter-scale changes in the shape of the ground surface, and announced publicly before fountaining begins. The gap between the moment the north vent starts overflowing and the moment 500-foot lava fountains are climbing toward an 18,000-foot plume is sometimes measured in hours. Those hours exist because scientists have spent decades building the monitoring network that makes this kind of forecasting possible. The eruption continues. The instruments are running. Episode 53 is live. Now picture the physical experience of what's actually happening inside Halemaʻumaʻu right now, because the numbers alone don't capture it. Halemaʻumaʻu is a crater within a caldera, a nested depression, a pit within the larger sunken summit of Kilauea, the crater rim surrounding the active. Vents has been closed to the public since 2007 because of the hazards along those edges: ground cracking, crater wall instability, rock falls, and during eruption episodes, the added danger of rim materials, hell itself slumping and sometimes exposing molten lava underneath. From the distant overlooks the park does make available, watching episode 53 means watching a vertical column of orange and red molten rock climb from ground level to the altitude where small aircraft fly, with a cauliflower-shaped plume of white and gray and ash billowing off the top and streaming southwest across an otherwise blue tropical sky. The ground trembles slightly with the seismic energy of the erupting vent. The sound, at permissible wing distances, arrives as a low roar. During Pele's hair events, when the wind is right and the fountaining intense enough to stretch ejected lava into filaments, fine glass threads drift sideways through the air like glowing copper wool carried on the trade winds, visible in the afternoon sunlight before they cool, darken, and settle on whatever surface they reach first. Those feeds attract tens of thousands of simultaneous viewers worldwide, making this one of the most widely watched active volcanic events in history. That accessibility, physical, since it's happening inside a national park visitors can actually reach, and digital, through the live camera network, is itself part of what makes this eruption historically distinctive. The Puʻuʻōʻō eruption of 1983 to 1986 occurred in a more remote stretch of the rift zone, far from established viewing areas. This eruption is happening at the summit inside one of the most visited national parks in the United States, in episodes that can be forecast days in advance. Inter-episode baseline. The gas disperses with wind and reacts photochemically in the atmosphere, and downwind fog conditions can shift within hours as wind direction changes. Communities in the Kau district southwest of the summit, including Ocean View, Pahala, and Naiaʻu, experience elevated fog concentrations during and after episodes, when the wind carries the plume their direction, exactly as it's doing during episode 53, with northeast winds pushing gas and ash southwest. Hawaii County Civil Defense Corps. This is the living environment of the active eruption zone on the Big Island in August 2026, a volcano that's now produced 53 high fountaining episodes in under 2 years, sitting above a mantle hoe. T-spot delivering magma at 25% above the long-term average rate. Scientists watch it with tilt meters, seismometers, GPS stations, webcams, gas sensors, and satellite imagery. They forecast the next episode several days before it starts. They issue alerts within minutes of precursory activity beginning, and then the volcano does WH. And it's always done what it was doing long before anyone stood on this island and watched it. It erupts, it fills the crater, it builds the cone, it sends glass threads into the trade winds. Episode 53 is the latest iteration of a process the planet has been running in this exact place for hundreds of thousands of years, and that the instruments arrayed around it have been measuring, documenting, and communicating to the public with genuine precision for the last several decades. Both of those things are true at once. The volcano doesn't answer to the instruments, but the instruments have made the volcano legible in ways that weren't possible a generation ago. That's what episode 53 looks like from the inside, and episode 54 will follow it on a schedule the tilt meters are already beginning to measure. As soon as pressure beneath the summit rises high enough to open the vent again and push molten rock back into the sky above Hawaii. There's one more dimension to this eruption worth mentioning, because it connects the immediate spectacle of episode 53 to the much longer story of this volcano and this island. In Hawaiian tradition, Kilauea is the home of Pele, the volcano deity whose creative and hands the science, but it shapes how communities on the Big Island relate to this eruption in ways alert levels and aviation color codes don't fully capture. The name Pele's hair, for the glass fibers drifting downwind from the vents, isn't arbitrary. It comes from a tradition of observation and relationship with this volcano that predates Western volcanology by centuries. When episode 53 sends those glass threads southwest on the trade winds, they're reaching communities that carry their own frameworks for understanding what the volcano is doing, frameworks that coexist with the USGS data and sometimes shape how people respond to it. For anyone planning to see the eruption in person, episode 53 illustrates both the opportunity and the difficulty of witnessing active fountaining at Kilauea. Most episodes since December 2024 have run under 12 hours, some consider a fly shorter. HVO's forecast window, typically a few days out, narrows as the eruption approaches, but the exact start time can't be pinned down until precursory activity actually begins. A visitor arriving during an inter-episode pause might wait 8 days for the next fountaining to start, or might arrive to find it already underway. The park's closest overlooks to the active vents may be open or closed, depending on real-time hazard condition. Send it northeast, toward Hilo instead. The volcano doesn't arrange itself for convenient viewing. It erupts when the pressure is sufficient, and stops when the reservoir empties, regardless of what anyone standing on the surface would prefer. Oblique as it happens. A 40-year-old record broken 6 episodes ago and still climbing. And a number, 53, that tells you exactly how far this eruption has already gone. It gives you no indication at all of when it's going to stop.